Good afternoon, everyone. I should say good evening. Thank you for being here to the very last slot of the conference, for having the patience of being here. So I'm going to talk about event sourcing. Just to understand, who was at the excellent presentation by Michael this morning about event sourcing? Okay, less than a half. The subject is the same. Possibly, I'm going to be more disruptive than Michael, as this talk comes from a real world project, a real experience I had a couple of years ago. It started a couple of years ago when I was working for another consultancy here in London. We started working on a client project, a new client project, where event sourcing fit perfectly, domain. But we quickly realized the mainstream approach to event sourcing, say the domain-driven design, the Greg Young approach, simply wouldn't work. So this presentation comes from that experience and some thoughts after that. Let's do a very quick introduction. My name is Lorenzo Nicora. I'm originally from Italy. I've been working here in London for 3 years now. I'm a platform engineer at Buildit, a London studio of Buildit that is part of Wipro Digital. In the last few years, I've been working essentially on microservices, cloud-native application, event-driven architecture, reactive thing. My main language since 2000 or something like that is Java, but I also used other languages. My main framework is Spring, but it's not the only one. I used Akka in Java. Very happy using it. And more recently, I'm using also Node and serverless, not in Java, of course. But this speech is not language related, absolutely. I will show no code, but a lot of drawing. So event sourcing, what is event sourcing? Who is familiar with the idea of event sourcing? Sorry. Okay, again, half, roughly, half of the room. Who is using event sourcing in an application, rather in a real application, maybe in production or close to production? 1, 2, 3, 4. Okay, few, but still someone. Just out of curiosity, of these 4 people, who is using an implementation based on domain-driven design? Oh, 1 is not using. Interesting. So most of the people using event sourcing is using an implementation based on domain-driven design. Nothing wrong with that. The point I will try to make is that might be also a slightly different way, another way that might work for some use cases, for some scenarios that are not so exotic. But another point, just to make the background, I will focus on scalability. So the idea is, for this presentation, is every application will be multi-node. So we'll have multiple nodes. We are not talking about a single monolithic, single node application. So we are talking about something that is supposed to scale on the cloud, usually, but doesn't really matter, but having multiple nodes distributing the load across the nodes. So distributed system, essentially. But let's start from the very beginning, from the legacy way of persistence. Well, we are still using it very successfully. There is nothing wrong in that. So we have a single application that processes both writes and reads in a synchronous way, so with a request response. Any request is processed through a transaction against a relational database. All the writes updates the state of our domain inside our database. And the queries hit exactly the same database. Everything works, everything is fine, everything is easy. That's fine. But at some point, we need to serve more clients. We need to serve more requests, so we have to scale our application. We all know that scaling out a relational database is not so easy. So the first option probably is scaling out our application. So adding multiple nodes doing exactly the same work. So distributing the client request across multiple nodes. But let's still work the same way. Request response, synchronous, transaction on the database, updating the database on every write. But here comes some problem when we start scaling massively, as ACID transactions requires locks that generates contention. And when our system becomes distributed, the effects of the contention and locks get even worse. And the information has to propagate across the network, even if it's a local network. And this harms the throughput and the latency of our system. So if we grow and grow, our database still represents the bottleneck. We cannot scale up just adding nodes. Our database is the bottleneck. So why not applying the reactive principle? Who is familiar with the reactive manifesto, reactive principle? Okay, well, many people. I'm not going to talk specifically about this. In a very short way, reactive manifesto says a way to scale up, or possibly the only way to scale up, is becoming asynchronous, is becoming message-based. The only way to scale up, keeping the application responsive, the latency reasonably low, is to become asynchronous. So why not using these principles? So let's go async. Let's treat our updates as fire and forget messages. So we have multiple nodes. We send them through, well, some form of message broker or something. Doesn't really matter. This message broker acts as a buffer. So reasonably, this part should scale very well, just hitting the peaks. And but we are still updating our database, our relational database. But there is a problem here, as the order of the updates actually matters. We cannot apply updates in a random order. It does count. If we accidentally, for many reasons that could happen, and it will happen when you have a distributed message-based system, we end up applying updates in the wrong way, we end up in the wrong order, we end up with an inconsistent state. And the problem is, when we are updating the state, we are losing information. So even if we find out we made a mistake at some point, we applied that to updates in the wrong order, it's done. We don't have the information to reconstruct our consistency afterward. So why not doing something I'm calling it's not correct? Let's call it update sourcing. Okay, it means let's treat updates as messages. Let's store them in a log structure, append only. We all know that regardless the database technology we have here, even relational database, the append only is the most efficient way of writing in any data store. And then we use this update to replay it through some form of business logic, doesn't matter, to rebuild the state and serve the reads. What we are doing here is implicitly applying the CQS, command query separation, or what is evolving into CQRS, command query responsibility segregation. The first one comes from the 80s, I think, the Eiffel language, while the latter is from Greg Young. CQRS is from Greg Young 5 years ago, something. But the general idea is having two systems, two parts of our system, if we're using microservices, could be separate services, serving writes, let's call them commands, and reads, let's call them queries. And in this case, the point of contrast between the two is our log of, let's call them update for the moment. But, sorry. So we have dropped our transaction, our ACID transaction, but we still have to enforce some form of consistency. And where are we enforcing consistency. So the domain-driven design idea that is excellent is using the aggregate. The aggregate is a cluster of domain objects that are treated as a single unit from the persistency point of view, but are also the unit of consistency. It means that one aggregate is one instance of an aggregate, one e-commerce order with a specific ID, moves from one consistent state to another consistent state, never to an inconsistent state. Typical examples are e-commerce, typical examples are bank account, do not allowing to withdraw more money than you have, and so on. Typical example. And so the domain-driven design approach, the mainstream approach to event sourcing, is receiving what we may now call commands, applying them to an aggregate, a specific aggregate. So this is a command of, say, submitting the e-commerce order. This is the e-commerce order aggregate. The aggregate is stateful, and the aggregate has the code that decides if this command is valid, what change of the state should happen, change the state, and then emit an event. And only then we are storing our event in a log structure. Let's call it event log or event store. Append only, that's fine. So the aggregate is stateful, we said. So if we lose the state of our aggregate that could stay in memory, for example, it's not a problem. We might replay all the events that refers to that aggregate, getting them from the event store, replay them, recreate the state, and then apply the next command. So, sorry, I'm repeating something Michael said this morning, but I need this concept to make my point. So we are making this distinction between commands and events. This is subtle, very important. The command is a sentence at the imperative tense. So it's a request, do this thing. And it's a request coming from the external world to our system, as it's a request, it's not a statement of fact. So this request could happen, could be applied, but also could be rejected, could fail for many reasons. We don't have the money in our account, so withdraw, rejected. From the flip side, the event is something that has happened. So it has been verified, is valid, has happened in the past. So by definition, cannot fail and cannot be rejected. It has happened, that's it. And in our approach, we are storing that thing. But for doing this, for applying this pattern, for transforming commands to events, we have each aggregate, as I already said, has to be stateful, as the transformation from one command to one or possibly one more event require the state of the aggregate. And also the aggregate has to be, don't misunderstand me, single-threaded. What it means is not the code being single-threaded, as one instance of an aggregate, that order, could process one command at a time. So that processing for that instance of the aggregate should be essentially one-threaded. And this makes aggregate look very close to the actors. I'm not talking about actors. If anyone who is not familiar, well, possibly many, with the actor models, I would recommend to have a look. It's something very interesting, even if you are not going to use. It's not by chance. Implementation of the of event sourcing based on domain-driven design works perfectly on actor-based model. But I'm not going to talk about this thing. Let's go ahead. So when we receive a command regarding an order we are lucky enough to have in memory, well, it's easy. We apply the command to our order, same key, we emit the event, store the event, done very quick. But if we are unlucky and we don't have that event in memory, what we have to do is retrieving the event, as I said, replaying them, rebuilding the state, and only at that point emitting the event and storing it. You may think this actually takes some time. So if you start thinking about something that has to scale a lot, okay, this is something that is slowing me down, rebuilding every time the state of our aggregate. But even more, if we are in a distributed system, so each box is a different node, we have to route, we have to find, the aggregate lives in one node only. Oh, well, this is one of the possibilities, or reasonable possibility. So our command has to reach exactly that node, not another one. So we have actually multiple options. The Axon framework is very smart on doing that. So one possibility is routing the command to the correct node. But it means our system has an additional step, and we are partitioning with some logic our aggregate across the nodes. And as every partition, when we had to scale out, auto-scaling for serving more requests, Black Friday, the peak, it works, it's fine, but re-partitioning is always painful in any distributed system. If you have worked with Kafka, if you have worked with Cassandra, when you add nodes, it works, nothing breaks, but it's a critical event in terms of performance, in terms of operation and everything. So could work, but it's not so easy. There are also other options actually, requiring some form of shared data store, in-memory data store, Redis, Seize, cost, name it. Implement is essentially a shared lock across the nodes, blocking any other node from processing one specific commands regarding one specific aggregate at a time. It's a global shared lock. Every time you heard about global lock, this should raise a red flag in terms of performance, in terms of scalability. So, okay, it could work, but it's not probably the best option. Distributed transaction, this kind of stuff, is not the best way of scaling. So far, we just mentioned the writes, but what about the reads? Well, very naive implementation. We have to retrieve the state of just one event. Well, it could be done this way. It's not the most efficient one. Could be done this way. Let's retrieve all events regarding that aggregate, replay all of them, build the state, return to the client. Not the top efficient, but could work. But when we have to query across the aggregate, for sure, this is not an option. Replay all events or possibly matching aggregates, possibly all aggregates of that type, rebuild them somewhere in memory in a different data store, query them to find the few matching the condition, and then return the few matching to the client. This is not efficient. It simply doesn't work. So the solution, and this is common to every event sourcing implementation, is using read models. Projection, there are many names around. Logically, they are the same thing. So the idea is using events and building an image of the state of our aggregate somewhere else, in a different data store, in memory, somewhere else. And the stream could come directly after processing the events or from the event log, depending on what you are doing. But you are building the state from events. And the point is, we might build this in some form of persistent data store, but might also be something else, not so persistent. Hazelcast, Redis, something we could lose. The point is, the event log is our source of truth, as at any point we may rebuild our read model from our event. So we may lose, or we may we may decide to drop the read model and rebuild it. But the other point is we are not actually creating one read model per aggregate. We are creating many of them using different technologies. More persistent, less persistent, Redis, Elastic Cache, name it, depending on the query you are planning to do. And also the data model of this read model will be different, optimized for different type of queries. So the general idea, we are building at least one, but usually more than one read model per aggregate set for serving different type of reads, different type of queries. So our read models represent the state of our domain for the rest of our system, for our user. So we have this picture of our domain to support user decision, to provide this information to other external system and so on. Every time you need to query, every time you need to read the state. And read models are based on events, so things that have happened. But let's ask one question. Where do this thing happen? In the model we described, with the aggregate transforming commands coming from the external world to events, these things happen inside our system and not in the external world. And we had to do it as our aggregate is supposed to enforce invariant, to enforce transactional. We are talking about business transactionality, not database transactionality. Our aggregate is supposed to enforce transactional consistency at write time. So we receive a command, a write, we enforce consistency at that point. The aggregate will never change from one state to another inconsistent state. And only if the change is valid, we emit the event. And only at that point, we write the event. So it's up to the aggregate to decide the event is correct or reject it. This approach works perfectly when your domain is very, let's call it process-driven. So, I mean, when your system has to drive a process, so you are logically receiving requests from the outer world, and you decide if that request is legit or not, and what is going to happen from that request. So you apply your consistency, emit your event, and you say, this is OK, this is KO. For all domains that are intrinsically very transactional, require strong consistency, not by chance, every example around is based on bank account, is based on e-commerce, or other examples like this. But there are also other types of domains out there. There are domains where our system is supposed to gather external events. And we still need to keep the events and rebuild the picture from them. And also, they are not necessarily related, but it happened to be both the thing. Often, we may have unreliable event sourcing. Let's think about IoT devices. How are they unreliable? They could be off on disconnected mobile applications. Not a fancy thing, but the mobile network is totally unreliable. The user could have an interaction, could have done something, and we receive that message later, or could be lost by accident. If you have ever messaged while in the underground, here in London there is no signal in the underground. In Milan we have signal in the underground, but not here in London. It's a mess. And this kind of domain are not strange thing. I would say many IoT domains behave like this. Many mobile applications have to behave disconnected. And in terms of type of domains, logistics and tracking, everything that have to track something happening and gather where the thing is, what has happened, parcel tracking, delivery tracking, all this kind of stuff, vehicle tracking. Well, specifically, the application I was mentioning was something for logistic tracking couriers and parcels and so on. In this kind of domains, things happen in the external world, not in our system. And what we have to do is gathering this thing that has happened and try to draw a picture that makes sense. But the problem is, as I said, the transport outside our system is not our system. Outside our system, the transport, the device is unreliable. So our messages could arrive late, could arrive completely out of order, could be lost. And the problem is, it's very hard to enforce consistency at this level. It's not an unreliability of our system. It's not an unreliability of the internal messaging system. It's the outer world. It's what happened here that is unreliable. So the general idea we started from, my colleague actually started thinking about this, is, okay, the problem is we have all this kind of unreliability out there. So we have the command, we have to enforce consistency at that level to meet events, but this relies on the fact of receiving commands in the right order. But we just said the mobile network is unreliable. And relies on the fact of receiving all commands, not losing them. Imagine if the parcel delivery, the parcel gets scanned before being put in the van with some device, then the courier goes to the door, deliver it, and say, okay, I've delivered. Let's imagine for some reason the first scan got lost. Could happen. What could we say? Could we just reject and say, no, you haven't delivered it? You can't do that. It has happened. We have to record it. And maybe we have to find out that there was some inconsistency and then react and do something out of band, somewhere, back office, I don't know. So the point is, stop trying to enforce, in these cases, stop trying to enforce consistency at right level. It also means essentially dropping the distinction between commands and events. Events happen in the outside world, and we receive them, and we have to accept them after validation and so on. But we cannot just reject an event and say, no, you're not, this is not valid. And the idea is thinking after when we start building the read models. So the general idea could be called write faster, think later. We have accept almost everything, write them in a log, never change it. Then we start building, then it means it's asynchronous. It happens at some point later, few milliseconds, minutes, doesn't matter, but later. This is totally asynchronous. When we start building the read models, we start thinking and we start saying, okay, there is something wrong here. And this mindset switch is not the same thing. I'm not saying it's the same thing, but is similar to the mindset switch you have to do when you're moving from the ACID transactionality of a relational database to the basic availability, soft state, eventual consistency of NoSQL distributed data store. Cassandra, Mongo, at some point, DynamoDB, name it. So it's a kind of the same mindset switch. So what we are doing here is having events everywhere, externally, internally. I'm naming them external and internal event, but it's not even necessary. What we do at that phase is a validation, mainly a security, just to avoid to have a forged message coming in, someone not authorized sending us a message. we check, don't know, signature, API key, something very basic. Okay, this message is alleged, is coming from a real device, not someone trying to send us event, and it's not malformed, it's not completely malformed, it's okay, and then we store it. But the real point here, this validation is absolutely stateless, and there is no need of having what I call the single-threaded aggregate. Again, single thread per aggregate instance, not single-threaded code, as there is no need of processing one event at a time, even for one target aggregate. And this improves a lot scalability, as in our distributed system, we may have any node processing any event coming in. Doesn't really matter. If we add more nodes, that's okay. We will have probably a load balancer or something here, just evenly distributing loads. And that's it. We don't have to repartition anything. And besides, so this becomes massively scalable. And besides, and this is not a characteristic of this implementation, this is true also for the other approach to event sourcing. If you put behind not a relational database for saving events, but some distributed data store, again, Cassandra, DynamoDB, something like that, that is designed to scale. The data model of this key value, or actually key value store, fits perfectly with event log. And this will scale much, much more, even if you have to process millions and millions of events. And this number looks huge. But when you start processing events from IoT devices, you easily comes to millions. In the case of that application, we were talking about 50 million messages a day in the typical day, in one day, and then you have the retention. Wasn't a huge thing. So the idea in this case, again, there is nothing wrong in the other approach, but if you have to face this kind of domains, this kind of problem, do not try to make sense of event on write when you receive commands, and be sure that events are absolutely consistent. But try to build consistent read models. And the good thing is, as we said, read models are weakly, even if they are persistent, they are weakly persistent. They are still built from the events stored in the event log. The event log doesn't change. You should never change the event log with all the things that Michael mentioned this morning, but generally speaking, the event never changes. So if at some point we find out that that read model for that aggregate was wrong, as we missed the message, we could rebuild it easily. Just drop it, replay the event of that specific aggregate, and recreate it. We have all information. But it's more than that. We may decide to reorder events afterward. We may decide to guess missing events. We may decide to rebuild the read model, not the entire read model, but for, say, that e-commerce order, for that parcel status, when we receive a late event. So we miss the scan event of that parcel, but accidentally we receive it, well, far later. At some point we said, oh, okay, this event was regarding this aggregate, but it's definitely late. Okay, let's ditch the state of this parcel, replay the events regarding that parcel, and now they are in order. We may also decide to delay read model on purpose to give event time to arrive. This idea is not very different from the concept of watermark. Watermark is a concept that comes from a white paper, I guess was from Google. The general idea is, I'm a bit simplifying it. The general idea is when we have a streaming system with events coming in, and we are building a picture with that, our messages are always from the past. And our messages takes time to arrive. And this time is, well, predictable, but not so much. So what we are doing is looking back to the past, as the messages are from the past, as it takes at least some milliseconds to reach us. But also, we know as this time is somehow unreliable, we can't look back closer than a given time. We are always look back beyond, say, 1 second ago, 1 minute ago, 10 minutes ago, depending on an estimate of the delay we might have. And this is not the delay of the propagation inside our system. If we are coping with mobile application, we might consider also an average time a mobile device could be disconnected, for example. And the flip side is building read models in this way, so applying thinking even more than you used to do with the other approach, takes time. This is not a massive issue. So we are already accepting read models are delayed, period. They are few milliseconds, seconds, but they will never represent the now. There is no now in any distributed system. But the good thing is this process happened completely out of band of writes, so different processes. In a microservice, different nodes. And they do not harm the performance of the write. And totally independent subsystem do not interfere. They might also scale independently. Different microservice building this read model, even one per read model. We have different performance requirements, scale them out selectively. One possibility of, for example, finding missing, lost event is using Saga. Saga is not something specifically of this approach. It's commonly used in event sourcing, well, also in other things. And the idea is having a stateful process. This is stateful, but is completely out of band, again, following the messages, the events regarding one process, one order, with a timeout, or more timeouts, and to be able to spot missing step in the business logic. And when we find it, after, well, a reasonable time, we found that, for example, the scan to the van was missing. After, say, 24 hours, we say, okay, someone should have scanned it if it has been delivered, definitely. No one complained about not delivering that parcel, so someone should have scanned. So let's submit a corrective event and say, okay, it has been scanned, maybe with a flag saying, okay, this is a guess, do something, but let's fix it. This is not a strange idea. This is actually what TFL does when we tap the contactless, also, I think the Oyster, not sure I'm using contactless, for getting into the tube. For who is not familiar with London, when you have a contactless or an Oyster card and you tap getting in and out from the tube or any transportation, well, you're sending messages essentially to the TFL. Sometimes this tap got missed. The reader doesn't work, many reasons. And the system is designed to be, it's not fail fast, it's letting you out even if it doesn't work. So what happened? At the end of the day, TFL misses some events. So what TFL does, actually, is not charging you immediately, but waiting, I don't know much, I think 12, 24 hours, usually the day after, guessing the missing event, and then charging you. They are rather smart. They check your commuting habit. Well, sometimes they get it wrong, but they're rather smart. And the idea is the same. the charge is based on a read model, is a picture of the reality of things that has happened. But there was something missing. They wait. After 24 hours, they are sure nothing will arrive, and they decide, okay, probably this tap was here. And they charge you. For doing this, for rebuilding consistency, the order of events is fundamental. But what is the right order of events? Seems stupid as a question, but it's not stupid at all. As well, of course, the order is, the events are ordered by timestamp. Which timestamp? There is no one timestamp in this kind of system. You have, inside your system, you have at least 3 timestamps that are slightly different, maybe very close if your system is fast, but you have a receive timestamp when you receive the message at the border, the processor timestamp when you validated it and processed, the stored, I made up these names, but the stored timestamp when the event is actually stored in the database. Of course, if your system is very fast, these are milliseconds apart, but they are different. So which one is true? Okay, but actually, the only meaningful timestamp is the timestamp put in the event from the source. That's the only one that makes sense. As we said, what happened here is totally unpredictable. We could receive the message when the guy got out of the tube, minutes later. But when the thing happened, when the message was written, when it was written. So when the device recorded the fact that the message was written or the button was pushed. So reordering events by receive timestamp, processor timestamp, storage timestamp is not meaningful. And this is a common order, a common mistake in many systems. As this, to be fair, is also valid for other approaches to event sourcing. The only ordering that makes sense is by timestamp put into the event from the device. But the problem is that timestamp is reliable only per device. So if we are lucky enough to have our business model where one device is equal one logical aggregate, I'm still referring to aggregate as a logical thing to represent, we are still representing one order, we are still representing the state of a parcel. I'm using the term aggregate in this way. So if we are lucky enough that we have this one-to-one relation, it's okay. So the local ordering of the events regarding one aggregate is sensible. Only one device will generate events regarding that aggregate. That's it. They will be in order unless the user is so crazy to change the clock. Could happen. We should consider it. But at least, on average, it's reliable. But if we are not so lucky and we don't have this one-to-one relation, device, event source, and aggregate, event ordering becomes not trivial. And there is no final question. There is no globally true event order always true. I'm not saying you can't order events, but you can't be 100% sure those events are in that order. You can guess, of course. You might decide, this is a possibility, to reorder events by causal relation, so causal consistency. It means if you know that for the business, this has to happen before this, the scan to the van has to happen before the delivery, and by accident, as it has been done by different devices, the timestamp are the other way around. When you start rebuilding the read model, you can say, okay, this is not possible. Someone was wrong. So made a guess, reorder them. To be fair, this is not trivial at all. The example I just did was the simplest one. In more complex cases, it's much, much harder. But this is a possible way. You should consider it. But the point is, there is no final, 100% sure event order globally. So, wrapping up. When you have in mind scalability, when you have to work, well, to scale with distributed system, could be microservices, could be not microservices, doesn't really count, but you have multiple nodes handling your traffic, and you have to do it to scale. But you still want to keep your latency reasonably low, especially the write latency. You cannot keep the client waiting. The write latency is the time measured from the moment we receive the message to the moment the message is safely stored somewhere where we will not lose it. So this is the write latency. And our business domain is not strongly transactional. Of course, if you had to implement a bank account, you can't do it. You have to, and the point is, keep the user waiting for things happening. But okay, there is no way around. But to be fair, in the real domain, not so many real domains have this strongly transactional requirement. Also, I would say most of the e-commerce and most of the bank are essentially eventually consistent. They have a lot of double checks to avoid wrong transaction, but they are all working on corrective transaction. But this is another subject. In this case, if you are facing these cases that is not so exotic, you actually have two possible approaches to event sourcing. The first one is the DDD approach. The one we mentioned, common through stateful aggregate becomes an aggregate. We store it in the event log, and when we have to rebuild the state of the aggregate, use the event log. This enforces transactional consistency at right time. Cool, works. Again, nothing against this. In this model, things happen inside our system. We are driving the process. We are reacting to commands from the external world we receive. In fact, this model works very well with process-centric system. We are driving the process. The problem is when we have to cope with unreliable event sources, unreliable devices, unreliable transport, and we have to scale out to big data sizes to serve many clients with peaks. Imagine in the logistics, when the courier start working at 6 o'clock or something, they all start at the same time working. So you have to serve a huge peak in the morning. And you have to keep latency low at that point. You have to trade consistency with latency. It's always a trade of consistency with latency when you are working with a distributed system. So in this case, these specific cases do not work very well with the, let's call traditional, it's funny to call traditional event sourcing approach. So you might try to think about a weak write consistency approach. Let's call it write fast, think later. So be lenient and stateless on write, validating statelessly the messages we are receiving. We are not receiving command, we are receiving events. And then enforce consistency when you are building read models. So you try to build consistent read model. The good thing is if you find out you make a mistake at some point later, you may rebuild the read model. In this approach, things happen outside our system, not inside our system. And our system, the goal of our system is drawing a picture of this external world. It's a totally different vision. This kind of approach scale out very well, a lot. Write latency could be kept very low. The main issue, apart from complexity, but to be fair, both approach have a lot of complexity. Apart from complexity, the main drawback, one of the main drawback is you always have delayed read model. The delay depends on your domain, your type of client, the delay or the reliability of your read model you are ready to accept and so on. You may also tune it. Not spending, this is just saying all the points in the same slide. I'm going to share it. I finished. I'm going to tweet these slides in minutes. You may mix the two approaches for different part of your system, different subdomain, if you think it makes sense. My last 2 cents, regardless the approach you decide to take, do not use event sourcing, regardless the approach, everywhere across your system for doing everything, also for user management. Do not use event sourcing when your use case is CRUD, unless you want to shoot your foot very heavily. So event sourcing is fine, works perfectly. Pick the implementation that fits your domain, your use case. Do not use it everywhere. Use it when it makes sense. And that's it. Thank you for your patience. Any questions?